in your whole lives for this moment. It's just too exciting. So, now we're into radicals. A radical expression is simply one that's involving the root sign with a radical sign. So basically the same rules of exponents still apply. I'm going to do out a couple of these rules just so that things are nice and clear, and we'll then use those going forward to figure out a couple of problems. If I have some number a times b under the radical sign, that's the same as saying taking the square root of the a times the square root of b. No problem. Same thing works with the division. If I have the square root of a over b, that's the same as taking the square root of a on its own and dividing it by the square root of b on its own. No problem. There are a few rules when we're simplifying these things that I've made note of in the lecture notes. For radical expressions to be in simplified form, we need for an nth root, there must be no nth powers as a factor inside the root. What do I mean by that? So, in essence, what that means is if you put it back into a fraction, could you simplify it? If I had some number x to the power of 3, and I was inside something to the 6th power, that would be the same as saying x to the power of 3 over 6, which simplifies down to 1/2. So in fact, to be simplified under the radical, we should have no powers inside. So when it says for an nth root, there must be no nth powers as a factor inside the root, that's what we mean. If you could turn it into a fraction and simplify it, you must do so. There are no fractions under the radical sign, which ultimately means that what it's looking for is this form, not that form. And if the expression is a fraction, there are no radicals in the denominator. So in the end, it doesn't even want that square root of b. And I'm going to show you how to deal with square roots or radical signs in the denominator through some examples, and you can see how to get rid of them. Okay, let's go through a couple of examples. So on that first thing, for an nth root, there should be no nth powers as a factor inside the root. So if we have something that's asking us to simplify the square root of 40, because of that implied 2 that goes in that check mark right in there, we're looking for anything where we can take out powers of 2. When we do that, or in order to do that, there's a couple of ways we can do this. I'm going to show you a quick way if you know how your times tables work. And if you're not as comfortable with your times tables, I'll show you a longer but guaranteed way at the same time. So 40 we can simply recognize as being 4 times 10. And the reason, there's a number of ways you can get to 40, but I choose that way because I know that 4 is a square, which is to say I can take the square root of it. Which means I'm getting the square root of 4 times the square root of 10. I take that square root of 4 and it's just 2. So I end up with 2 root 10. The other way I could do this, if I'm not quite as comfortable with all of that, is I can do what's called a factor tree. I'm going to do this in a different color just so that it's clear that it's a different process. And with a factor tree, you're just trying to break things down to all of its smallest basic factors. So 40, it's an even number, so I'll divide it by 2, which will leave me with 20. 20 also divides by 2, which leaves you with 10. 10 divides by 2, and that leaves me with 5. ultimately, these are the numbers that I'm interested in, the ones at the end of the branches, and I'm looking for pairs of numbers. Okay, because of the implied 2 there, I am looking for pairs of numbers. Do this in black. There's a pair of numbers. Okay, there's a pair of 2s, so I can bring those out and just call those one of the 2s. I have no other pairs, so these numbers stay inside my radical. Okay, so I end up with 2 to the power of 2 times, and then radical 2 times 5. I can put my 2 times 5 together, and again I end up with 2 radical 10. So your pairs, one can come outside. Anything that isn't a pair stays on the inside. I'm going to do that one more time, this time with a cube root, so you can see what happens if it's not just pairs. So this time I'm going to ask for the cube root of 24. So now instead of looking for pairs, I'm looking for groupings of 3. If you can figure these things out in your head fairly quickly, it's fine. So we're going to take the square root of 24, and we will recognize that that can be broken down to 3 times 8. Square root of 3, or sorry, cube root. This is cube roots everywhere. Cube root of 3 times the cube root of 8. The cube root of 8 is 2 times 2 times 2, so just 2. And then we leave the cube root of 3 there. If that's not as obvious to you, again, we can break it down as a factor tree. 24 divides by 2, and it leaves me with 12. 12 divides by 2, leaves me with 6. 6 divides by 2, and it leaves me with 3. When I look at it, there's a grouping of 3, so I can bring one of those outside, and then that 3 stays inside. So I end up with 2 cube root 3. Sorry, I'm being told the camera's a little out of focus. Let me see what I can do here. That's worse. Too far. Is that better? If I made things worse? Sort of the same. Let's see what I can do here. And yes, I will try and write things bigger so that my exponent 2s and exponent 3s are just a little bit more clear. I'll try and do it bigger. Let me rewrite this bigger, and you'll tell me if that works. So let's go with cube root 24. So cube root 24 becomes cube root 3 times cube root 8, which just becomes 2 cube root 3. Is that better? Okay. Okay, so now let's move on and take a look at what happens when we have radicals in our denominator. Sorry, why does it become a 2? It becomes a 2 because 8 is 2 times 2 times 2. So we have groups of 3, okay? So that 8 could become 2 times 2 times 2. Because it's groups of 3, we can bring it outside. We can take its cube root. Is that clear? What happens if we're given something like the square root of 5 over 2? Well, as we were looking at earlier, that's the same as saying the square root of 5 over square root of 2. However, we're not allowed to have radicals in the bottom of our fractions. So I'm going to get rid of it. How do I get rid of it? I'm going to multiply it by itself, top and bottom. Because when I do that, square root of 2 times the square root of 2, I'm just left with 2. Those square roots cancel each other out. And then on top, well, 5 times 2 is 10. So now I've gotten rid of that radical on the bottom. It's not always that easy, but we're going to start with it that easy and go from there. The other thing that we want to start to notice about radicals is that they function a lot like questions where you're asked to gather like terms. Okay, so anything that's got the same radical on it can be collected. What do I mean by all that? So let's say we have square root 75, square root 20, plus the square root of 12, plus the square root of 45. First thing I'm going to do is I'm going to simplify all of these. I'm going to do it the fast way. If you have questions about where something came from, do ask me and I will try to clarify it. So 75 is the same as saying 3 times 25. 25 is a perfect square, so it can come down to 5 square root 3. Square root of 20 is the same as saying the square root of 4 times 5. I can take the square root of 4, and it's a 2. Square root of 12 is the same as saying the square root of 4 times 3. Again, I can take that square root of 4, and it leaves the 3 behind. And then the square root of 45 is 9 times 5. I can take the square root of 9, and the 5 comes along. So just to be clear, square root of 25 becomes 5. Square root of 4 becomes 2. Square root of 4 becomes 2. And the square root of 9 becomes 3. Now that I've done that, I look for things where I can put stuff together. So in this case, my 3's, I got 2 things where the square root of 3, so I can put the 5 and the 2 together. And I end up with 7 root 3. Same thing happens with my square root 5's. I can put, those are the same, so I can put these together. And I end up with 5 square root 5. And then there's nothing else that simplifies, so we're done. One more worked example. Combining the two ideas, how do we rationalize the denominator, which is to say, how do we get rid of the radical on the denominator while still simplifying all of our radicals? And in this case, our question is going to read square root of 6 plus the square root of 7 all over square root of 8. First thing I can do is I can simplify that one. That's as simple as it gets. There are no squares hidden in 6. There are no squares hidden in 7. But there is a square hidden in 8. It's 4. So this becomes square root of 6 plus the square root of 7 all over 2 root 2. Those of you who are wondering what happened there, this became square root of 2 times 4, and then the 4 was a square, so it came out over there. So now I can take my root 6 plus root 7 over 2 square root 2, and I go, oh, I have a radical on the denominator. I'm not allowed to do that. So this is going to multiply by square root of 2, top and bottom. And when we do that, I end up with square root of 6 times the square root of 2 plus the square root of 7 times the square root of 2 all over 2 square root 2 times the square root of 2. But we can simplify all of this now, and I end up with square root of 12 plus the square root of 14 all over 2 times 2. We're not quite done. We need to clean this up a little bit. I'm going to bring it back up to the top just because I've run out of room. So I'm here. I've got square root of 12 plus the square root of 14 over 2 times 2. Well, there's a square hidden in 12. It's 4 times 3. There is no roots hidden in 14, however, so it stays on its own, and 2 times 2 becomes 4 on the bottom. I can take the square root of 4, so it becomes 2 root 3. Square root of 14 is as simple as it can get, so we leave it alone, and then 4 stays on the bottom. Now, for those of you who are probably wondering, why am I not simplifying the 2 here? The reason I cannot simplify this 2 with this 4 is because I don't have anything corresponding on the other radical. The number in front of this here is a 1, so it doesn't divide by 2 nicely. Because I can't divide everything by 2, I divide nothing by 2. Okay. Unless there are any more questions on that, I'm going to keep moving. I want to get to a point where I can give you guys a chance to stretch and have a break, and then we'll do some questions. All of the previous requirements for exponential expressions to be simplified still apply as we move forward, and this is now the default rule. As we move forward on these tests, you'll be expected to be able to simplify radicals and to rationalize the denominator, which is to say, get rid of the radicals on the denominator. And no negative exponents. So we will do one more quick example just so that you can see how something must end up. And then I want to go back to trigonometry just for a quick question so you can see how our use of radicals helps our trigonometry. Then we'll take a brief break. So let's pretend we've just done a fairly long, involved problem. We've simplified everything down, and we get to this point, we go, oh, okay, we're done. And the answer is no, we are not done. We have bunches of problems. We have a huge radical over an entire fraction. We're not allowed to have that. We have negatives in our question. We're not allowed to have that. And at the end, we want to make sure we have no radicals in our denominator. So, whole bunches of pieces of work to be done. First thing we're going to do is we're going to get rid of that negative exponent. That negative exponent says it wants to go to the other side of the fraction line. So I'm going to take my 27, I'm going to leave it on top, and I'm going to end up with y x to the 5th on the bottom. Next thing I'm going to do is I'm going to break out my radicals. So I end up with square root of 27 on top, and I end up with the square root of y x to the 5th on the bottom. Now this x to the 5th has a couple of squares in it that I can pull out. Just do a quick sidebar here. X to the 5th is the same as saying x to the 4th times x. And if I have this under a radical sign, I can then take the square root of x to the 4th, and the square root of x to the 4th is x squared. So I end up with an x squared times x. That's how that comes about. So on the bottom here, I end up with x squared on the outside, and then x and y on the inside. At the same time, I can take a look at 27, and I'll do the same sort of sidebar. And 27 is the same as saying 3 times 9. I can take the square root of 9, and I end up with 3 root 3. So that's what I get here. Now we're very close to being done. But again, we have this radical on the bottom here. We don't want that radical on the bottom. So I'm going to multiply by x square root of xy, top and bottom. And when I do that, on the top, I end up with 3. Everything under the radical multiplies together, so I end up with 3xy. It's getting a little squished, sorry. And then on the bottom, the radical is what cancels out, so I end up with x squared times xy, which is to say x cubed times y. Okay. Any questions on that? Sorry. So what happens here? I'm actually gonna erase the upper stuff, and I'm gonna spread this out and explain it out in a little bit more detail, just so that people can see it. So I'm here, I'm at 3 square root 3 over x squared root xy. And this is being multiplied by xy over, or root xy over root xy. When we do this, we're of course multiplying straight across. So the 3 just comes along for the ride. That's no big deal. Root 3 times root xy all comes together, and I end up with 3xy. That's no problem. On the denominator, what we end up with, and if I do this out in excruciating detail, we're going to go with the x squared comes for the ride. Square root xy times square root xy ends up being square root x squared y squared. The top is just going to continue to come for the ride for a little while, so that's 3xy. The x squared comes along. I can take the square root of x squared, it's x. I can take the square root of y squared, it's y. Again, the numerator, the top comes for the ride, 3xy. X squared times x gets me my x cubed, and then the y comes along. Does that clarify for everybody? Why is the x squared equals, okay, so square root of x squared, the way one wants to think of this, I think I'm looking at the right one. If I have an x squared under the radical sign, the squared and the radical cancel each other out. Yes. Cool. Okay, one more quick example. I figured there's got to be a bunch of people who are ready to stand up and stretch for a minute. So let me go through the last little thing that I just wanted to explain. When I was talking about trigonometry last, one of the things that I mentioned was with our special triangles, we can't just write things the way they come up. So a quick recall on our special triangle. If I have, let's do this bigger so it's clearer here. If I have 30 degrees there, 60 degrees there, and a right angle there, I should have 1 root 3 and 2. Yes. Okay, so that's our special triangle. We end up with this root 3. So if you're dealing with, let's say, just for a quick example, cosine of 30 degrees. Remembering our SOHCAHTOA, this, by the way, is a good habit. Whenever you're dealing with a trigonometry question, you're not quite sure where you're going. First thing you should really do, write down your SOHCAHTOA so that you can remember what all of your relationships are. Okay, so I've just written down cosine so I can remind myself, oh right, cosine is adjacent over hypotenuse. So there's my adjacent, and there's my hypotenuse. This becomes nice and easy. I end up with root 3 over 2. No problem. My radical's on top, not an issue. But let's say I'm dealing with the tangent of 30. Tangent is opposite over adjacent. So now, that's my opposite, that's my adjacent. So I end up with 1 over square root of 3. And that's what we're not allowed to have, is that square root of 3 on the bottom. So it is sort of taken as given because that's the way it reads when you just put it out, that what you are going to do is you're going to rationalize that denominator automatically in your head, so that the answer we actually come out with should be root 3 over 3. So if somebody's asking for the tan of 30, you're looking at your special triangles, you want to automatically convert it to that form. Okay, and the same thing holds with your other special triangle, your 45-45 triangle. Or that's 1, and that's the square root of 2. That's your hypotenuse, which means that for the sine of 45 and for the cosine of 45, you would end up with your radical on the bottom. Like that, and that's not how we want it. In the end, how we want it should be root 2 over 2. Okay. Last thing to show you on all of this goes with the Pythagorean theorem. I'll do a quick example. We can now continuously have exact answers when we're doing something like this. So we're given a triangle, 3, 15, some unknown. Our Pythagorean theorem, of course, a squared plus b squared is equal to c squared. So I will take it as a, b, c. 3 squared plus x squared equals 15 squared, so 9 plus x squared is equal to 225. X squared, sorry, we'll just do this really quickly, minus 9 is equal to 216. Now we can actually take care of this properly. So now I'm going to take the square root of my x squared, and that's going to be take that away, and I then need the square root of 216. Without going through the full factor tree on this, this is the same as saying 6 times 36. I can take the square root of 36. I end up with 6 root 6. So that's the exact answer. Okay, it is 10 to 6. We have half an hour left. I've had some requests to take a look at a couple of questions from the homework for trigonometry, so I'm prepared to go ahead and do that. If anybody else has questions in the trigonometry they would like me to go over, feel free to get those prepared. And in the meantime, I'll let everybody take a 5-minute break. So I will start up again at 5:55.